So now in previous uh, video, like I revised the some concept of digital part, which actually basically the number system basically. Now I jump into a new chapter that is combinational circuit. So okay, so now try to solve or understanding the combinational circuit. So basically, combinational circuit, internal connections of logic gates. Basically, maybe it's a AND gate or gate or combine of logic gates, and you make a circuit. That is basically the combinational circuit. So there are n number of inputs or n number of outputs, and uh, outputs can be. So present output depends on the present input only. So there are no like such as previous output that goes into the input of any circuit. So basically the present input you are providing and the output also behave as on the present input. And design example, so here is design a circuit to detect decimal number 5 to 10 in a 4-bit carry code. So G3, G2, G1 and G0. So basically decimal detect decimal number 5 to 10 in a 4-bit carry code. Okay. So from 5, so 5 like 5 to 10. Okay. 1 0 1 0, that is my 10, and 5 is 0 1 0 1. So from 5 to 10 we need to decide a circuit. Okay. Let's make a circuit which actually 5 to 10. So it's a 4 input, like 4 bit. So we go through a KMF. Here is my KMF, and here is my, suppose bit is 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. That is my AB and CD. So if my AB and CD, so basically from 5, so it's my 0 1 2 3 4 5 5. Here is 5 1, because I write here, and if I go through red pen, so okay, just 5 7 6. Here something on, here 3, here 2. 6 6 7 8 9 10 11 12 13 14 15. So I need a 10. So from 5 to 10. Okay. So 5 to 10, I need a like this 5 to 10, 5 6 7. This is, so if I change the color, suppose I am doing green color, then this is, or if I do the red one, this is my 576. And if I do the box, so mm, box, add box, draw figure, add save here. This is my one box. Basically, this is my 576. This one and this part. This part is my another. So I another square. Take it. So 8 9 10. Basically, so little bit I make the, so basically not 12. So basically this is my circuit. So here this part, this box and this box. So I need to give one. So it's detect the my decimal number. Okay. So basically here is my one box I make, that is 1 0. So something like that. If my input is like here, input is my G0, G1, G2. So I assume my MSB is G3. Okay, so G3, and here is G3 G2, that is one, and G3 G2, and what is this? This is my mm, like this circuit we need. So what's the G3? Because my A is G3, B is G2, and C is G1, and D is G0. So that here is G2. Sorry, G2, not G2. G2, here G3 bar G2, and what is the here what is common? Basically, the common is nothing, so you will take two this and two this. Okay, so G3 G2 G3 G2, and here is one, so my is here is D, means G naught, and if we take another plus, so G3 bar G2, and this is my G1. So this the circuit we need. So what is the output? So that's the way you can solve, and using K-map. So this is my how this can be G3 G2, so MSP we need 5 6 7 9 10. But how it would be, I think they change the circuit, I think. Circuit implementation, so how they can G3 G2, so 0 0, so 0 1 0 0, that is basically 4. So 0 1 0 0, that is basically 4. 4, but 4 is not here. Okay, in this gray code, like design a circuit to detect decimal number 5 to 10 in a U bit 4-bit gray code. Okay, 4-bit gray code is present in a 4-bit gray code. Okay, and that's why the circuit is little bit different. So that's why the group is here. So basically, design a circuit to detect a decimal number 5 to 10 in a 4-bit. Okay, gray code. So then that's why the circuit is different. Okay, I don't understood the like I am not. I was not read the question carefully, so that I did the mistake. So just do this in another way. Like I was right, but the questions is basically I understood forget to understood in a right way. Like so, so here is my box. Here is so gray code, for gray code my circuit would be like this: 0 1 2 2 3. Just a second, it's saving the PDF. 2 3 4 5 6 7 8 9 10 11. So 5 to 10. So this is my circuit way. Like this is I my KMap. So this is KMap. So obviously this is my output, and here is the circuit you can make like this way. So design a circuit to detect decimal number 13579 in a 4-bit 5 to 1 BCD code input. 5 to 1 BCD code input. Okay, let's make. So here is my 5 to 1 1. Okay, this is my circuit. So basically A B C D. So 1 3. Yes. 5 to 1, so 0 0 0 0 0 0 0 1. It goes to basically 1. So here is 1. How to make 3? 5 to 1 1 like this way. So if we make, see, here is my output. Here is 0, no output. Here is 0 0 1 0. So this would be not possible because I needed 2. So here 5 plus 2 plus 1. So this is my another case. If it would be another case, okay, another way we can write here 0. So my output is 1. Why 1? Because in here 1, so total is 1. So in here also 1. And if my 0 0 um 1 1, so what is my output? My output, so 1 3, this is my 2. So this is not, 2 is not there, so it is 0. My output is, if my input is 0 0, oh sorry, 1 0, so in this case my output is 0. Like this way we can do 0 1 0 1. So 2 plus 1, this is my output 1, and 0 1 1 0, this is also 1. So like this way we can solve this. So 0 1 1 1. So this is my 5, 2 plus 1 3, 3 plus 1 4. So no, there is no 4. So this is 0. And now 1 0 0 0. So this is my 1, means this is my 5. So 4 then 1. So now 6, like 1 0 0 1. This is my 0. And also 1 0 1 0. This is my output also 0 because it's 6. So now 1 0 1 1. So this is my 5 plus 2 7. So this is my output 1. And if I write 1 1 0 0, so this is my 5 2 1 1. So 5 plus 2 7. This is also 7. My so output is 1. And 1 1 0 1. So this is my output is 8. 8. So it's not, it's 0. So 1 1 1 0. This is also 0 because 8. 1 1 1 1. So this is my 5 to 7 7 to 9. So this is my 9. So this is my 1. If I go through the K map, so how I make, so what is my ABCD? So if I go to the K map, so here I make K map. Okay, so here is I make K map A B C D. So here is 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. So my first is 0. So here is in this position, this is my 0. So this is not required. So 0 0 1. So G triple 0 1. So double 0 1. Here is my 1. Okay, just wait for a second. Okay, now I can write here 1, here 1, and here so G double 0 1 0, double 0 1 0 also 1, double 0 1 0. Here is 1. So here is 1, and okay, here don't require it, it's 0, it's 0. Here 0 1 0 1. So 0 1 0 1, 0 1 0 1. So 0 1 0 1. Here is my 1. So I will cut this here again. If I write here, okay. So actually confused a little bit which output is which one. So if I take this, 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 okay. Now confusion is not clear. Actually, here the problems little bit created. Okay. So if I check my, so here is 0 also. If I check, or 0 1 1 0 0 1 like this 0 1 1 0 0 1 here is 0 0 1 1 0. So basically this this is my one. So 1 0. Now this is 0, so don't require. So 1 0 double 0 1 0 double 0. So here is my 1 1 0 double 0. This is my 1, this is 0, this is 0, and here is 1 0 double 1 1 1 0 double 1. This is my 1, so it should be also we can cut. Now 1 1 0 0. Oh, is my 1 1 1 1 0 0. So this is my 1, this is cut, this is cut, and this is my 1. So we can make like 2 here, 2 works here, 2 works here, 2 works here, and 2 works here. So that's the way we can make the circuit. So and I think here is the answer. So now minimize, and this is the your circuit implementation. So basically in most of the case, while you used or the problem ask from combinational circuit, just apply K-map and you will find the short answer. So that is the basically that is the way we can solve the combinational problem. So yeah, like everywhere you find most of the question like they give a black box and you define the circuit according to the input and according to the output, like what the output they required. So according and also input is available, so according to the output you need to define the circuit. So basically just in a combinational case, just um, apply the map and you will find the answer, easily get the answer. So design a combinational circuit which produce 2s complement of a 4-bit binary number, ignores sign bit. Okay, design a complement circuit which produce 2s complement of a 4-bit binary number. Okay, 2s complement of a, so how I can make? So 2s complement is basically ignore sign bit. Okay, 2s complement of any number, ignore sign bit. Okay, suppose my 2s complement is 1's complement plus 1. So how to make 1's complement plus 1? 1's complement is basically NOT gate. So if my 0 1 0 1, so if I doing not here we do not, so we get 0 1 0 1 plus 1. So okay, so this is my um, not yet. So I need a here I need a one adder, one half adder. So that's enough. And rest of the this part is I need to make a NOT gate. So in NOT gate, how I do? So basically, this circuit would be look like this. So my A is here. So one NOT gate circuit is converted. One NOT gate B converted. C also same like that converted, and D something like that converted. Now what I do that suppose I number get a just a second, that is A, like it's I assume this is A, this is B, this is C, this is D, so it's small. So what I did, that I need a half adder. Half adder, like every gate we pass, suppose the carry, suppose my circuit is 1 1 1 1, we had a 1, so what I get, so 1 1 0 1 0 1 1 0 and 1 1 0, just like this. So and 1, so this will be discard no matter what, but the thing is how many half adder I required. So basically here I take a half adder, so the input is here and I gave one input as a carry, and these half adder one required, so C directly put, and here and this directly put and here, and this directly the carry output, and here is my output. So output is y3, y2, y1 and y0. So half adder circuit is required 4, and a NOT gate is here required. So I think this is the way to you can implement, and let's check. So how to implement this circuit? So basically the y3 for case, this the way you can also implement, but the idea is that so 0 0 2 is complement, that 2 is complement is also 0 0 0 1, so 2 is complement is something like that. Okay, and y1 he got, so y1 basically a bar b bar c bar d bar a bar b plus a bar d bar. Yes, you can also, this is the way you can do. So for y0 it's like nothing, y0 equal to 0 basically, y0 equal to 0 or something like that, something other. So y0, in case of y0, what is my y0? Okay, y0 1 2 3 4 5 6 7 8. So there are something, so y0 basically d. If y0 is d, okay, y0 whatever the input that goes to output 0. Yes, so no problem. 1 1 0 1 1 1 1 here 1. So yeah, you can thus the way also solve the problem. Basically, if you know the know about how to make ADA circuit, so it's ADA circuit, or like basically this problem is actually one previously I done, that is make a circuit. You can do both subtractions and addition. So we just use a marks. So choose the negative. Like suppose for addition, I want to addition. So a plus b. So what we did that a is directly put the full adder. Okay, and here is marks. So and b is like b. This is positive b. So this is go positive b, and one this here. This is my minus b. So that's the way we select the marks and choose the input. So if I do a minus b subtraction, so what do we do? A plus of minus b, or minus b is what? Basically 2's complement of b. So 2's complement of b, so that's the way we can do. Like first we not the abcd, then just add 1, and that's the way we can do. So basically this is the problem. But here also like go through k-map by using k-map, like where is y3 is 1 1, abcd is my minimized. This is also a good type of thing. So here the like not gate, that what I already told, that not gate is required. Not gate is required everywhere, and same for y1 and y2. So here one is black box is also present. So the question is, design a combinational circuit which produce one's complement of a 4-bit binary number. Ignore sign bit. Design a combinational circuit which produce one's complement of a 4-bit binary number. So one is complement of 4-bit binary number, that is pretty much easy. So suppose my 0 0 0 0. So your output this. If your input is 0 0 0 1, then what is your output? Your output is 1 1 1 0. So just it's a not gate, like a not. Here you can see, and probably y3 equal to, you can see here. Okay, so this is your not gate type of things, and here is circuit place, circuit implementation. So how you can implement the circuit? Just simple take not. Design a combinational circuit which take 3-bit binary input and produce output equal to the square of the input in binary form. Okay, the you need to make a square circuit. So how to make square? Okay, it's pretty much easy. So if you 0, 0, 0, 0, 0, 1, so 0 square means 0, 0, 0. And how is your maximum number? That is your maximum number is 7, that is 49. If your maximum number is 7 and your square is 49, so 49 how can you represent? So basically we need to represent by actually 6 bit required, because in 5 up to 5 bit you can represent 32, and in 6 bit you represent 64 up to. So that 49 is greater than 32 and less than 64. So basically that's why you need to like 6 bit required. Okay, so 6 bit 0, 0, 0, and for 1 is also 0, 0, 0, 0, 1. For 2, 0, 1, 0, so 0, 1, 0, 2 is 0, 0, 0, 4, 1, 0, 0. That's the we can solve. And after that, here y5 like something is 1, so that time you just so y5 equal to only once time added, that is come, that is I think abc, where abc both are 1. So and also in 1, 1, 0 like 6, 36, so here is only two case 6 and 7, and you just make the circuit y6 equal to abc ab, y0 equal to c, y1 equal to 0, y2 equal to b c bar, y4 equal to a b bar, and y3 equal to a xor b, and multiply into c. So this is just basically you make a k map. Here the here the like number, here is your input number, and here is your output bit, and y5 where is 1, that you put on the k map like 6 and 7. That's the way you can make. Here is another question, that is design a combinational circuit which takes two 2-bit binary input and produce a single output. The output will be the output will be high when the decimal equivalent input is binary sum of the binary sum of input is. Okay, design a combinational circuit which takes 2-bit and produces single output. The output will be high when the decimal equivalent of the input is binary sum of the. Okay, so basically it's like just like a behave like a comparator circuit, but the I think when is one. Okay, so here is the circuit for the bring the sum. The input is the bring sum of the input is whatever. Design a combinational circuit which take 2-bit binary input and produce a single output. The output will be high when decimal equivalent of the input is basically decimal equivalent. So here also can decimal equivalent sum. I think the question is a little bit different here. You make a y0, y2. Basically, it should be a1, a0 like this, and y0, y2. This is my yb, and find output control input if c equal to 0, y equal to y0, x or y2, and c is equal to 1. Then my y equal to y0, x nor y2. Basically, this question is little bit, I think, problem something. Okay, leave it. This question, like everything is same. Just if combinational circuit questions comes, just read and whatever the requirement according to the requirement, you need to design the black box basically. So in black box, just where the output is 1, so that only go through the k map and go through the k map, and there where your input is like input of the circuit, and that's the way you can make the circuit by designing by a logic gate. For 3-bit input, design a combinational circuit which detects majority number of ones or majority number of zeros. Okay, first majority number of ones or minority number of zeros. 3-bit input. Okay, it's easy, very pretty much easy questions. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So detect the circuit. First is majority of 1, so majority of 1, and minority of 0, so I take the small 0. Here's my output. So majority of 1, where is my majority of 1? Okay, actually basically this I want to remove. So here is my majority of 1 and minority of 0. So majority of 1, I a majority of 1. So here is majority of 1. This is 1. So here before that 3 zeros. So here is majority of 1. Here not. Here is majority of 1. Here is majority of 1. Here is majority of 1. And minority of zeros. So the higher is majority of 1s. So that is also my minority of zeros. Because that's why the circuit like add is a complementary circuit. So here's like in minority of zeros, where is minority of zeros is greater. So here is minority of zeros is 1, here 1, here 1, here is 0, here 1, just complementary ones another. So that's the way you can solve A and B part. So here is 1, just take the so like go through the k map. So here is my k map. So first is 0, 1, 2, 3, 4, 5, 6, 7. So here is my 3 is so 3 is this, and 4 not 4, 5, 6, 7, 5, 6, 7. So this is my like this way we can make a box, and here we the M1 we got, And how to solve aim not. Here again, go through K-map, and here is my M1, here is my M0. So 0, 0, 1 and 2, 0, 1, 2, and what is this? So just a second, charge is not that much. Okay, so 0. So what is this here? Here is my 3 and 1 is I hope where is 1? This is my 1. So what is this? So this is my 1. So this is my fourth position. So fourth is here. So you can just do the combination of make. Here is 1 and here is 1. So you just like go through by this way. Just make K map and whatever they want to ask. So this is my aim not. This is my aim not. As you can see here. Here is aim not and here is my aim1. Where is aim1? I did mistake. What I did mistake. No, not possible here. Majority number of zeros or minority number of ones. So this is my circuit. What is the problem with this? Okay, okay. Yes, this is the circuit. Then what is this circuit and what is this circuit basically? This is the circuit I got here. And this is the circuit of this and this. And okay. And what is the circuit of this? These three are same. Okay, whatever. That's the we can solve now. So conclusion, majority of one is detector, minority majority of number of zeros detector. So this is my conclusion and this is my basically circuit here. This is my circuit. Like what's the input required and what's number of gate and which kind of gate is required. So basically this tells everything about the circuit. And now is code converters. So what is code converter? So design a 4-bit binary to gray code converter. Okay, so binary to gray code is simple. So basically you need to, that's we already studied that how to make a binary to gray code converter. So previously I also told that here we take a number. Suppose my number is for binary b3, b2, b1 and b0. So if your like remembering power is not that much, so you go through this way. You just write like kmap, first make kmap, then like first make kmap, and then write basically what is the problem. Okay, I think where is the free space. Okay, first make a kmap. Like if you forget the how to write binary to gray and gray to binary, okay, no problem. So this is your kmap. So just write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So this way you can write your gray code. So this here gray code 0, 1, 2. Sorry, this is not 2. Okay, so basically you first binary to gray, so that's why you first 0, 1, 2, 3 like this way. So that's why. But the actual position, what is your zeroth position, so binary 0 also. One position 1 also. Tooth position, that is 3, binary 3. Three position, that is 2. And seventh position, that is 4. Sixth position, that is your 5. Fourth position, that is 6. Five position, that is 7. So just check whether is where your 5 is present. So here is 5, and 5 what represent? 5 should be represent your 7. Like okay, just a second. So 0, 4, 4 is here, 5. So 5 represent must be 6, not 6 or 7. Okay, so here 0 is 7. So 5 is 7. 0, 1, 2, 3, 4, 5. 5 should be 6, but here I don't know how to. Yes, binary. Just to check the circuit, 0, 1, 0, 1. So here I have doubt. So 0 is 0, 0, 1, that is my 1, 1, 0, that is my 1, 1, 1, that is my 0. So I don't know what's the problem. Like he done mistake. I think this should be 0. So 1, 1, 0. 4 is 6. How 4 can be 6 here? 0, 1, 0, 0. So if you write binary to gray, this is my 0, 1, 1, 0, 1, 1, 0, 1. I think he did little bit mistake maybe, but design a 4-bit binary to gray code converter. Okay, just a check on Google. I think here it is mistake a little bit, but let me check. Binary to gray code. And here is my gray to binary and binary to gray code conversion. Okay. Okay, so 101. This is my ABCD and this is my binary code. So 101 and this is 7. How it is 7? 4-bit gray code. So basically 101. This is 7. Here so should write the 7. Okay, let me check another way. Maybe I am wrong, but like yeah, obviously I am wrong. And how is right? 101 0. So 0, that is 0, and now if I take 1 1 1 0, that is 1, and 0 1. So okay, this is my binary converter. 5. How to possible like 5 bit it is be 7. 0 1 2 3 4 5. Okay, 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 understood, understood, understood. I think what I make mistake in 5 here, so it is 7, right? So what is your 5 number, and if I took the 4 5 here, that would be 6. Uh, but this is binary code. Binary code. Okay, if I make a, so here is my binary code. So this is my binary number 0, 1. Sorry, not 2 here. 2 here, 3 here, 4 here, 5 here, 6 here, 7 here, 8 here, 9 here, 10 here, 11 here, 12, 13, 14, and 15. If I now write my gray code, so if I write my gray code is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that, so the confusion start from here. Little bit confusion. So binary to gray code conversion. The binary to gray code convert is a logic circuit that converts the binary code into its equivalent gray code by putting the MSB1 below axis and the MSB1 above it axis, reflecting the n-1 bit code about axis after 2 to the power n-1 rows. We can update the n-bit gray code. The 4-bit binary to gray code conversion table as below. Okay. So we, okay, this is my binary code. So if we go through K map, then what's the problem? So 0, 0, 1, 1, 2, 3. So if I need a 3, 3. So basically, where is my 5? 0, 1, 0, 1. So if I see my binary number, then what this should be my gray code, but the problem is this is not. Your gray code should be here 0, 1, 1, 1, 7. So this is my gray. Then what is my gray code to binary? Okay, gray to binary conversion. Now check gray to binary. 4-bit gray to binary. Let's check from here. Okay, binary code, then XOR of 2 and gray code like this. This is my C programming, but to binary code. Not this one, binary gray code. What is this? Mm, mm. If your gray code is like 4, then 1, 1, 0, 0, 0, then it would be 6. If my this is my gray code. If 4 is my gray code, then my binary number is this. Okay, and if my 5 is my is 7. Then what I need I require this is my like suppose gray code GC. Then what's I need gray code 2 1 0 0 1 1. This is my 5. So 5 is my binary number. So basically here 0, so 0 1 0 1. So for understanding purpose, if here is 7, so this is my gray code and this is my binary number. Okay, this is my gray code of this binary number. Now I understood. Suppose my binary number is 0101. Okay, then what is my gray code? Gray code 011101 011. So this is the equivalent. Now I understood that if suppose 7 is my gray code, then what is the binary number of 7? That is 5. If my 5 is so here this is my gray code. Basically, in KMap, what the fault that what I had fault or misunderstanding that I thought this is my binary number, so that if my binary number is this, then my gray code is this, but this is not. So if my binary number is 101 something 0101, so if my binary number is this, then what's my gray code? So for gray code 0 and 0 like something like this 1011 101 and 011. So this is my if my binary number is 5, so gray code is 7. If my gray code is 7, so gray code is like anything like 111, I assume my gray code. Then what is my binary number? So then it is 1 here. This one goes to 110. This 01 represent me 1. This 10 represent me 1. So this is my gray code. Gray code that is my 14. And what is this number? That is my I think 11 I think 8 to 10 11. So let's check. So 11 is my binary number and 14 is my uh 14 is what? So 11 is my where is 11? 11 is here. 11 is here. sorry, 14 is my gray code. So here is 14. 14 is here. 14 is gray code and 11 is my binary number. Okay, now I understood that 14 is my gray code and 11 is my binary number. So whatever the I wrote in 11 in red, so this is the concept. Okay, little bit misunderstanding previously I had, so now it's clear. So basically, if you had a K map, okay. So the problem is here is by suppose 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, it's not 8, 9. 8, 9, 11, 10, 12, 13, 15, 14. So if I write my, this is my actually, okay, I'll tell you what is this. So now this is 0, 1, 2, 3. Here is actually I did mistake a little bit. 0, 1, not 2, 3, 2. So basically if I write in a red pen, so then it is my 2, 3. Here is my 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So whatever I marked here, this is my gray code and this is my binary number of this gray code. This is my gray code, this is my binary number of this gray code. This is my gray code and this is the binary number, that is 4. I think here is 4. This is my 7 is gray code and 5 is the binary number of that gray code. Okay, now I understood everything. So whatever I wrote in blue, so that is my uh, gray code, and whatever I wrote in red, that is my basically binary number of that gray code, and also vice versa, we can say. So now I understood the concept. Okay, let's go again the skin mirroring. But okay, I think this part is missing, but so I repeat again. So whatever I wrote in red, that is my actually binary number, and what is my uh, wrote in what is I wrote in blue, that is my uh, gray number. So this is 5 is the binary number of this 7. Okay, this 7 means this gray code 7. Now what again, PDF. And we know the how to make the binary to gray. So here is, if my binary code is like this, so how to make gray code? For gray code, okay, same in PDF again, just like this one, and just put first one and then XOR this right here 0, XOR this right here 0, XOR this right here 0. So this is my binary and this is my gray. Okay, so let's check what is the uh, 8 gray code. So first check, here is my 15, that is my binary number, and this is my gray code. Okay, and if I would check it's vice versa or not, so I had 1 0 0. If I 1, then it is 1 directly, and this one goes to XOR with this 0, and this is 1 again, something like that. So 1. Okay, now the concept is clear, and you can make the circuit easily now. So here the circuit, gray to B3, gray to binary converter. This is my circuit, that's I already told. So design a 4-bit BCD to X XS3 converter. Design a 4-bit BCD. 4-bit BCD to XS3 converter. So how to make? So for in BCD, my number goes to 0 to 9. But what is the number? Like 0. For 0, okay. Just check how to make the circuit. So for design a 4-bit BCD to XS3 converter. Okay. So BCD number, what is my BCD number? Basically it goes to 0, 0, 0 to 9. So just write it. Sorry. And if we write XS3, so 0, 0, what is the XS3 code of this? So that is basically my 3. Just start with like add 3 like this type of things. 1, 0, 0. So that if I would 1, 0, 1, 0, that is 1, 0, 1, 1, 1, 1, 1, 0, 0. Okay, this is my BCD and this is my XS3. And if I want to make a XS3 code, so suppose this is my, I gave the name that is um, XS3. So I E1, E3, E2, E1 and E0. I give the name and here is B3, B2, B1 and B0. So just here the last one and from that's the way like we make E3 key map. That is my key map. Here is my key map. So 0 and what we did the after 9, so we take the cross. So if required then you can take, otherwise not necessary. Sometimes it's your bit is more required if we take the unnecessary of the this kind of gate, so don't care type of gate. Okay, so here you can make, I just make one gate that is E3. Okay, so E3 is from start from 5, 5, 6, 7 and also 8, 9, 10, 8, 9, 8, 9, 10, 11, 12, 13, 14, 15. So we can make like this. Here we can make a gate, make a 4, and here we can make a 4, and here we can make a 4. Okay, so this is type of thing. So E3, for E3 case, just see whatever I, okay. So one thing I missed, that is basically we take also 8 pin. So sometimes it's like problem, but okay, you can also take here how I change. Okay, here is one gate, here is your second, and here is your third. Okay. That's the way you can do, and everything you can do. Now a 4-bit binary code, B3, B2, B1 has been converted into BCD code. Okay, A3, A2, 4-bit, A3, A2, A1, A0, C3, C2, C1, C0, BCD code. Expression C2 can be expressed. It's simple actually, basically. Suppose your binary binary, so 0 for 0, what do you write in binary? That is 0 0 0 0. And what do you write in, okay, here is the list here. So you need to convert your binary number into BCD. That's all. So here you can write 0. 0 is my decimal number. So 0 0 0 0 is your binary, and BCD. For BCD, you need to represent like when is 15. 15 how we represent? So that is your 0 0 0 1 5 0 1 0 1. So basically you need to maximum 6 bit. 6 bit is 5 bit also enough. Okay, so how many bits he takes? He takes the A3, A2, A1, A0, C3, C2, C1. Okay, he took 8 bit. Okay, no problem. Okay, so here is my A3, A2, A1, A0, then C3, C2, C1, C0. So I write A3, A2, A1, A0, C3, C2, C1, C0. And here I take B3, B2, B1 and B0. Okay, this is my 0 0 0 1. So basically one decimal and same as now two decimal. So up to 9 we don't have any problem. But if we example 10, so 10 how binary, it is simple 1 0 1 0. But in BCD what happened? That BCD 1 0. So 1 represent 0 0 1. Sorry, 0 0 1, and 0 is like this way. So 0 0 0 1 0 0 0 0. So this is method up to. And if we suppose write 1 1 0 0, that is my 12. So how to write 12? So 0 0 0 1 and 2 0 0 1 0. This the way he wrote. And here is the things. Imagine, like not imagine, like just see here. It is 12. So how is 0 0 1 0? How one? Oh, it's not 12. It's actually 10. So he wrote. Okay. Here is 12. How many wrote? 0 0 1. So this is 12. So I think I mistake. No, I also write. Here is 12. So here C3 and example of 7 segment display. So how to represent 7 segment display? Basically 7 segment display is nothing but like here you can see the structure, that is the display, like this. Total 7 LEDs are there. That's why its name is 7 segment. So in 7 segment you can represent all the bit basically, and it goes to 0 1 2 3 4 5 6 7 up to 9. So how to make? So design a circuit that detects the number that uses lower left segment in 7 segment display for a 4-bit BCD code input. Okay, it's a 4-bit BCD code input, so it's simple basically. So basically A is here, B is here, C is here, C is here, D is here. So A, B, C, D, E, F, G. Okay. So this is my 7-7 display. Don't go like don't judge me about like don't judge me about my like skill my drawing skill. Like don't judge me of the skill of my drawing. Okay. Actually, also don't judge me by my communication skill in English. ABC D E F G. I think this is the question. This is the thing. Yes, this is the things. And here, so I need to represent zero. So when it is zero, zero. This is my zero. So only F is missing here. Here term is missing. Rest of the all are okay. So here is my A B. Okay, I took the some other's name. That is AB I already took. So P Q R S. This is my number, BCD number. And this is my A B C D E F and G. So this is my 0 0 0. If you want to 0, then except F. All the bits are 1. Okay, this is 0. And if it is 1, but how to make a 7 segment display by using PCD? So what the circuit it would be? Okay, it's simple actually. So now it is 1. So I take 1 1 here. So my DE can be 1 also or BC can be also, but I can DE. Okay. So your input is P. So how to glow? Okay, so A is my output, so here is A. So I took from that like and I minimize through Kmap, and that's the way you can solve it. And thus have an output from there, and we take the okay. And here is some particular number. I think he told us. So we had only A, B, C, D, A. So A, B, C, D. So 0 0 can I make? Design circuit that the number that is lower left segment. Okay, like this segment, which circuit will be? Okay, 0 is there, 2 is like this, so 2 can also be there, 3, 3 is not 3, 4, no, 5, no, 6, 8, so 0 to 6, 8, 0 to 6, 8, okay. I was thought how to make like 7, 7 display. Now this is by parity generator and checker. Parity generator and checker. So to detect the error is the data line. Okay, noise, error, and digital communication. This is the part of, so 1011 RX and TX. That is my channel RX TX the parity. So an extra bit with the transmitted signal which tell us the number of ones does not tell anything about number of zero. So to detect, so an extra bit with the transmitted signal which tells us the number of one is okay, and the number of zeros does not tell everything about number of zeros. Even parity makes the number of ones even. Odd parity makes the number of ones odd. Okay, parity and data line, parity and data line. Okay, and here is parity and data line. Here is parity and data line. So even, and here is odd. Even parity and odd parity. So parity generator, and here is parity generator, here is transmitter, and here is receiver. Okay, and 2 bit even parity generator, that is D1 D1 D not D1. So 00 01 10 11, and odd parity, that is number of ones, number of ones. 0 is even, 1 is odd, 1 is odd, 2 is even, and here is 2 even. Okay, two-bit odd parity generator, odd parity generator. Odd parity generator. So first go to the convo. Like what is odd parity generator? Makes the number of ones even. So everything is even. Then even parity, parity and data line, parity on data line. So here is even. If even numbers of one, then it's even parity, and then odd number of parity. But how it is? Okay, parity generator. Parity bit P will be 1 if number of ones are odd. Odd number of ones detector equal to 1. P will be 1 if number of ones are odd and odd number of ones are detector XOR. And here the XOR. So now what's the 2 bit even parity checker? Number of ones. So even parity checker, that is 0. Here is number of ones. So where even number of 1, then its output is 0. Higher odd number 1, then its output is 1. And 2 bit odd parity checker. So basically when odd number of 0, then is 1. Here is 1. Here is 1. Odd number of 0. Here is 1. Here is 0. Here is 1. Here is 1. So 3 bit even parity generator equal to here 3 bit odd parity generator. This 3 bit even parity checker, 3 bit odd parity checker. Okay, 3 bit even parity generator. So for generator case, number of ones odd, number of ones odd, output 1, odd number of ones detector, XOR gate. So parity generator and parity checker are both are different things. So basically number of ones, that is 0 even. Here is 1 number of odd, even parity, but here is even parity, so number of ones odd, that is called even parity. Here number of ones odd. Okay, if one, if odd, then output 1. Odd number of ones detector. Okay, it is called also even parity generator. So generator means it's also called. Okay, just the concept is opposite. And a 3 bit odd parity generator. So higher like odd parity, so odd number of like 1 is there, so there is 0. Even parity, so there is odd number of 1, that's why it's even parity. There is odd number of 1. It's little bit confusing. Let's check on even parity and odd parity. Google generator. Even an odd parity generator. So let's check what is the introductions. Okay, 3-bit message parity bit. So basically it's a even parity generator. Okay, in even parity generator, so when my odd number of 1 is present, so here is not odd number, here is odd, but here it will also be data line. This is something should be 1. Okay, that's the reason I think. No, but it should be like even parity. So okay, so here we check again. If even parity generator, then let us assume a 3-bit message to transmit the parity bit. The 3-bit A, B, C constitute the message are the input to the circuit. The parity bit P is the output. For even parity, the P must be generated so as to make the total number of ones including P. Even the circuit diagram of even parity generator so along with the Boolean expression for even parity generator in table 1. The parity bit is 1 when the total number of ones even as whole including parity bit. Okay. So 3-bit message is here 0 0 0 0 0 1. So while odd number of is 1, that times it's 1. So that basically it is called odd parity, even parity generator. Here is even number of those, so that's why it's 0. Here it is also 0. Here it is 1. Here it is 1. So it's like a an odd parity generator. So when my even number of ones present, so this is called my even parity generator. So this is my higher is even number of 1, that is 1, otherwise it's a 0. So this is my odd parity generator. And what's the other concept is like parity checker, odd and even parity checker. So that's for odd parity checker. We paired with checker. Now generator and checker. So what is digital signal processing? An additional bit either 0 or 1 is added to the original binary signal code to detect and correct any kind of errors in the data that can occur during transmission. This addition bit is called parity bit. The addition of parity bit to the original digital code makes the total number of ones the code either even or odd. Thus, on the basis of number, one is the data. The parity can be classified into two types, namely even parity and odd parity. If we add a 0 or 1 to the original binary code and this makes the total number of ones in the code an even number, then it is called an even parity. And on the other hand, we code and this makes total number of ones code and called an odd parity. So the parity bit 1. Okay, how does parity bit works? So decimal digit. So even parity BCD. So even number of this is like parity bit. This is what parity bit generator. Okay, the parity bit generator, and this is my parity bit. I think checker. Maybe let's check. So in parity bit checker, even parity. Okay, here is a big odd parity generator. Here it is. This code is a one and parity generator. Even parity generator. So even parity generator. This is my odd parity generator and checker. Checker is where this is my checker. Even parity checker. So when even number of zeros are present, even number of zeros are present. So this is 0 and output is 0. And my even number of similarly 4-bit message how to understand. So let us now 4-bit consider a 4-bit when even number of zeros are present, so my output is 0. When my even number of Ooh, so what is P? P is basically parity checker, I think. Like this. So even number of zeros, then my output is 1 and 4-bit code with parity. Okay. So here is my even number of zeros, so 1. Even number of zeros, so 1. Odd number of zeros, 0. Okay. This is my checker, and this is my also odd parity checker. So odd parity checker. So when is odd number of zeros, then my output is 1. Here is my even number of, so 0 0, and here is my odd number. And if generator case, so that there's like we check the 1. So if even number of 1, then that is odd parity generator. And if my uh, odd number of 1 is present, then that is my even parity generator. So just opposite. And in case of uh, checker, parity checker, so there's we like detect the 0, how many zeros are present. So if it is even, then like my this is called even parity checker, and if the zeros is odd, then that is called odd parity checker. Okay. Now, so almost 98 page, and here is the two parity even parity generator checker. So this is we already done, and in the next video or lecture I would start from 100 100 page. Okay, bye. Here is stop recording.